that what you do in your office? Just scroll through Reddit? Or you have to go to class?
Huh? No, I saw it yesterday night. Yeah, I read it.
Huh?
I jump on that cheated math and that learn math, and I give help.
Really?
Times in.
Dude, I could actually do that right now. I could just sit.
I'll just subscribe to it.
Keep reminding myself it's mostly like young dudes, so I'll get the weirdest freaking responses sometimes. I'm like, oh, that's right. I remember being that way.
Do you mind if I play Borderlands?
You do what? You gotta play Borderlands?
Yeah.
Yeah?
Yeah.
Maybe I should do it.
There you go.
Huh?
Yeah.
Classic.
I'll be right. Everybody else is like, just do something, Jeff. God, what are you talking about up there? All right, we're going to get into section 3.1. And 3.1 kind of goes back over some stuff we've talked a little bit about before. It gets really deep into quadratic functions. Chapter 3 in general is going to be graphing. And I don't know if I've said this here. I know this. I told this to my 110 students at 176. I don't say this to be anything other than fully open. 176 pre-calculus is graphing hell. We're going to study the hell out of graphs, and you're all like, yes. All right, so we're going to learn a lot of little shortcuts, a lot of little what the hell does it mean, a lot of little what do I see in a function and how does that translate visually. Because when you go into calculus, even if you're not, I don't care, you still got to pass this class. But if you're going into calculus, you want the graph to be right there so you can learn the calculus and not have any problems with graphically what's going on. You with me? So that's why we call this pre-calculus. Now, so quadratic functions, of course, ones like that. We can talk about quadratic and form, but we're going to stick with this for right now. The what's called the standard form of a parabola. Standard form. It's like this. That's the standard form for a parabola. It's sort of related to mx plus b for a line. Because in this form, I could tell the most important things about the parabola. So what's going to determine whether it opens up or down?
It's a sign of
A. If it's negative, it's going to open down. If it's positive, it's going to open up. So that's a lot like the slope. That's very related. It's not the slope. This is the parabola. It's a curve. So you're going to need calculus to talk about its slope. But it is related to the slope. The bigger it is, the quicker it goes up, so the skinnier the parabola gets, right? And if it's 1/2 or 1/3 or 1/8, then it's going to get fat. It's going to go up really slow. You guys kind of with me? So in that sense, this is very much like the slope, which is good, because this is where the slope would be. What the hell's going on here? If I had this function, what kind of a shift would this be?
no shift.
It'd be to the right.
Okay, good. And h itself could be negative. So we'll just say left or right. H. And then this would be up or down.
K.
In fact, I'll be really careful. K. Okay, so we'll see why I put answer value just to take the negatives out in case it is. So it's left or right, H, up or down, K. So the vertex for this one is located where? 0, 0. So the vertex for this one is going to be located
There.
there being what? H, comma, K. I love it. Because I'm going to shift 0, 0 by this much. So if I put this into that form, I can just see its vertex, and I can see if it's up or down and how fat or skinny it is. Right? So that's why if I put it in the mx plus b form, I can see a line, slope, and y-intercept, which are its two most important things. You guys kind of... So how the hell would I take something that looks like this? For example, if I had this, and I want to put it into this form, how would I do that?
Complete the square.
Complete the square. I know when I want to make something look like this, I know it's going to be completing the square. Now, completing the square, I don't know if you remember this, it only works when the first number is a 1. Yeah. So what sucks about this? Let me move the -1 way out of the way. Move the -1 way out of the way, right? What do you want to do with this piece? You got to do what? You got to take a 2 out. And then you're left with. Okay, and then leave a little bit of room there so I can complete the guy's square. How are we doing so far?
Good.
So how do you complete the square? You take half of 4 is
2 squared.
2 squared is
Bring back
4. It's crazy. So then here I want to put.
+4.
And here's where things get a little weird. You got to stay with me now. If I put a +4 right there, see how there's a 4x?
Mm-hmm.
Is that a 4x really for the function?
No.
No, it's really 8x. But the stupid 2 I took out of it doesn't really show me what it really is. It's twice that. So if I put a +4, what did I really just do?
Put an 8.
I added 8.
So you want.
So what I got to do out here at the same time, Indiana Jones? I got to undo what I just did. If I put 8 there, I got to do -8 there. So overall, I didn't do anything. So if I want to put the sand on there, I got to at the same time got to move the golden statue out of the way, right? And then run the boulder and all this kind of shit. That's what happens in math all the time. Do you guys see that? This is going to happen to you. So then this is twice what? Good. The whole reason we just did all the business was so I can write it like this. -8, 9. So is this going to be up or down? Up, because it's +2. Is it going to be skinnier or fatter than a standard? Skinnier, because it rises twice as quickly, right? So it's going to be a little skinnier. Goes up faster. And where's the vertex? Careful. -2. -9. Remember, if it's in with the variable, it's the opposite. If it's out there, what does it do to that? It takes it down 9, right? The whole transformation thing we did earlier explains why that vertex works like that, yeah.
So when you get the 8 outside the parentheses, you have to do the opposite, right? Like the negative?
Yeah. I mean, we know that already. We know that if I had f of x equals square root of x -8, what would happen to this? It would take this down 8. So this would take this guy down 9, and that would move it over back 2, right? So the vertex would go there. The vertex used to be at 0, 0, so now it's -2, -9. So does that sort of feel like, it doesn't exactly, because the work is a lot more complicated because they got squares in there, but I'm putting it into like mx plus b form in the same kind of idea. Once it's in the right form, and just like a circle, once it's in the right form, I can see all the most important parts of it. Okay, good. So you're definitely going to have problems like that. I've already talked about how to find the vertex, the shortcut. Did we talk about why that works? What is the shortcut for finding a vertex? Yeah. So one way to find the vertex is to put it into standard form, and then you can see the vertex. And then the big mistake people make on this is, what's this guy's y-intercept?
0.
See, I set some of you guys up. I set you up. I'm sorry. You spoke up, which is good. Speaking of was good. Why is that not good? If you put a 0 in, what do you get?
2.
2 squared is 4 times 2 is 8 minus 9 is -1. And why does that make sense? Look back at the original. That's where you can see that, right? Because here the x's die if you put a 0 in. Here, if you put a 0 in, there's stuff left there, shit. So if you put it in this form, you can see the vertex, and you can see other stuff, but you can't see the other stuff you used to seeing easily. Does that make sense? So there are some drawbacks to this form. It's hard to get there, and I suddenly picked the wrong y-intercept. And the picture looks freaky as hell if you do that. How you guys doing? All right. Okay. So the shortcut. So thank God there's a shortcut to find the vertex. And not surprisingly, the shortcut is related to the shortcut for completing the square itself. The shortcut to completing the square to solve an equation is the what? Who remembers? The shortcut to completing the square to find a solution to a quadratic equation is called the quadratic formula. That's the shortcut, believe it or not. That's where it came from. I'm pretty sure
How is that a shortcut?
that is totally a shortcut. Not always, I agree with you. Sometimes it is quicker to do this. But I mean, if I had 11x squared plus 9.2x minus 14.789, quadratic formula kicks this guy's ass, right? I don't want to deal with all that crap and do the completeness square on that. No. How we doing? Okay. So, who remembers? Did anybody say this? Who remembers what the shortcut was? Beautiful. So if I have something in this form, the vertex is going to be at negative b over 2a. That's going to be the x piece. So to find the y piece, I just take that and plug it back in, right? If I know an x piece, I just plug it in and get the y piece, right? We've talked about that before, I'm pretty sure, yes.
So once you find the vertex there, you could use that to find, to that formula.
You could. Good. I love it. That's awesome. But if I ask you to put it in standard form, I better see this work. Right?
So you're saying the vertex, that's you're figuring out x, and then you put x back in.
Yes, so let's try it on this guy. What would the shortcut say about this guy? X equals negative b, negative 8 over twice a. Yeah, negative 8 divided by 4 is negative 2. Looks good so far. And if I plug a negative 2 in to this guy, it'll be twice negative 2 squared plus 8 times negative 2 minus 1. I get 4 times 2 is 8, minus 16 is negative 8, minus 1 is negative 9. Kick ass. I think we all agree that that was definitely a lot shorter than that was, right? Maybe not in the amount of paper taken, but it's definitely in work done. Maybe. Now, why does this work? That's beautiful. That takes so much ass. But why does it work?
Because it's part of the quadratic formula.
Beautiful. Because remember, if I knew the intercepts for a parabola, where would the vertex have to be?
Right in the middle.
Right in the middle. So we have talked about this before, right? So that negative b over 2a is what's right in the middle from the quadratic formula. And what does the quadratic formula do for a parabola? It finds all of its x-intercepts. Even if they're complex, it still doesn't matter. Okay. So a lot of that should be review. This might not be the most review-ish thing, but you should have done something like this before. We're back. What's going to be a little new is our first foray into true you're going to love what I said. So it's true pre-calculus word problems, optimization problems. Oh yes, we've done word problems, but that was review. That was old algebra word problems. That was pre-calculus word problems. Right? The pre-calculus word problems are not overly evil. They're optimization problems. And I know you guys are not going to believe me, but that's all right. Optimization problems. That's the name of the game too. Question. Pre-calc word problem. And here's what I mean. Here's a very simple example. If I had the profit function for a company, look like this. Sure. Where X is the number of, hot dogs they sell at Bless you. And P, of course, would be the profit. What's one thing that definitely makes sense about this function visually?
Got a maximum.
Yeah, you would hope to God your quadratic that represents your profit would be an upward facing, because then you could just make as much profit as you make, sell some more. Yay! Right? But of course, if you make more, the costs eventually kind of overrun the, so there's some sweet spot right in the middle. Some sweet spot right in the middle, and that's what this captures. So not all profit functions in the real world are exactly like this, but they all kind of have the same idea. They're going to have these, and they might have multiple maximums, and maybe some maximum is easier to get to than some other ones. But anyway, it's all basically the same idea. How do I find this guy's max?
Calculator.
Find the vertex.
So if you want to get points for it, how do you find this guy?
Find the vertex.
Find the vertex. How do you find the vertex? Yeah, so the whole, whenever you have an optimization problem, it says find the maximum area that can do this. Find the minimum cost to make this kind of thing. Find the max or min, whatever. You're gonna have to get a quadratic equation, and then you just find its max or min, which is the vertex, right? In calculus, you can do this work with any function here. Any function you can imagine I put there, calculus can find its max and min if they exist, right? But for us, we're like, that's nice calculus. All we can do is freaking find the vertex of a parabola because we haven't studied what the hell slope does. But how do I find this guy's vertex?
Negative b over 2a.
Yeah, so it's located at x equal negative b over twice a.
200.
200. So I got to sell 200 hot dogs. And then how much money? Hopefully it's not negative. I don't know. I just made this out of nowhere. It has a really good chance of being. No, it's not going to be negative. It's good. All right, it'll be 2, 0, 0, 0, 0. 26,000.
46.
What is it?
I got 46.
That's cool. I don't trust my brain totally. So if you put a 200 in there, you get negative 200 squared
400.
plus 400 times 200. So that would leave 200 200s plus 600. Yeah, 200 200. There you go. 46. So what do you get? $46,000. That's awesome, man. I don't know how much they sell these dogs for. I don't know what they're made out of. They have little gold flecks in them.
What if they're brats?
Oh, even better. Even better.
Let's make them bigger.
Even better. Alright, but you guys get the idea? Sort of? Because I'm going to leash you on a problem here right now. So on page 231.
You said what page?
231.
231. I'll start you off nice. Problem number 65.
What number?
65. Did anybody come in and not get their test back yet? Make corrections in that, just like the quiz. Like, notice some of the easiest mistake. What do you think is the easiest mistake somebody could make on this?
Switch up A and B.
Yeah, they don't identify B and A correctly. Just because they put the x squared second doesn't mean that suddenly it's B. Then negative 0.4 is still A, because it's in front of the x squared. You guys with me? So A is always in front of the x squared, B is always in front of the x, and C is the number that's by itself. In this case, it's 0, but who cares? Alright, so how do you set this up? Negative B over twice negative 0.4. So you get negative what? It should be positive. 100.
100.
Yeah, that's better. Yeah, 80 divided by 0.8 is 800 divided by 8 is 100. Yeah, I think if you do, you got to be careful when you plug this in the calculator. You can't do 80 divided by 2 times 0.4. What goes wrong there?
Divides
It doesn't. The 0.4 would be on the top then. So if you want to put in the calculator all at once, you got to do that. Make sure the calculator knows what the bottom is. Calculator doesn't have eyes. You can't see this bar. We can. So thankfully, we still have an advantage over the machines at the moment. All right. So it's the maximum revenue occurs when they sell 100 whatever the hell's. Right? They don't tell us what they're selling you there. Units. I love it. There's AC units. And then how much revenue would they make if they sold 100 units? Just plug 100 in. And you get who?
4,000.
4,000? 4,000? Okay, we'll take your word for it. That's 4, so these.
8,000 minus 4,000 is 4,000.
What? Yep, this is true. It's amazing how it works. Okay. So this will be 8,000
Minus 4,000.
minus 4,000.
Equals 4,000.
Oh, okay. No. All right, cool. That's not bad. Especially if they gave you the function, right? So what about one when they don't? You know, that's the real word problem. That's not even a word problem. That thing is not a word problem. That's a plug-in sheet. No big deal. So what about number, like 7? Well, they give you the function. That's not good. Here. Sorry. Ooh, 76 is gross. I like it. I can't remember if I signed that. I must have. Let's try 75. They give you too much, but at least they don't give you the function itself.
Which one?
75. The one about the horses. Horses.
No, you assigned 76.
Good. All right. Some of you guys might, going into this problem, you might know what shape will always maximize, what quadrilateral shape will always maximize the area. Square will. knowing that doesn't mean you're exempt from doing the work. You just know what the answer should come out to be. Right? If I were to put that against a river, and I have some animal that does not swim, so I don't need to put a fence there, then that's not going to be a square anymore. You kind of with me? But if I just have it all the way around and want to maximize the area, I make a square out of it that maximizes the area. Now to go beyond that, what shape are bins on these farms, so like peanut farms and all that kind of stuff? What shape do those bins take? What shape do they have? Cylindrical, right? Because a circle, it took me a while to figure out how to say it, a circle will always be better than a square when I have something that can fill up all at once. So when I have little peanuts or something, I definitely want to make it circular. I'll have to use less material to have an equal sized volume on the inside. Does that make sense? And people just kind of naturally discovered this. So then they made these cylindrical shapes, and math came in and said, "Oh yeah, you're doing good." For this problem, what's the function we're working with? Part A. Say what? What's the area of that?
Length times width.
Length times width. So it'll be
1200x.
so 1200x minus x squared. Therefore, you know that this has a what kind of area? Max or min? It opens down, so it's got a max, which correlates to part B asking us to find the max, right? So if you create a function that is an up parabola, and the next question says find the maximum, you know you did something wrong, right? This doesn't have a maximum. It goes forever up. It's no good. Yes?
And what do you do with the 2,400 feet of fencing?
They kind of use that to create this. Do you see what the perimeter would be? If that's x, that has to be 1,200 minus x.
Oh, yeah.
So that's got 2,400 all the way around. So this is the most general rectangle out of 2,400. So I would not have given you this picture. You would have made your own picture, right? So I would not have done this much work for you. So I'm not nice. So what about this, guys? Now I want to find the max area for part B. So in general, if I want to find the max anything, I have to first create its function. I hope to God it's quadratic, right? Because we're only in pre-calc. We can't do it any more than that. It is quadratic. So how do you find the max area? Okay, that's good. So good start. So that would be negative 1,200 divided by twice. Negative 1, cool. 600. What's up?
Plug 600 into
Yeah, so then find an area, just plug the 600 in. And then a quick way to do it is 1,200 minus 600 is 600 times 600 is
36. A lot of numbers.
Gotcha. Which relates to this being a square. Find the dimensions. So this is the area. What are the dimensions? Were they going to be 600 by 600? They're going to be a square.
So just because it says rectangle, it means it can be a square?
Well, what's a square? A square is a rectangle. It's just a special rectangle where the sides happen to be equal to equal. Yeah. Yes, sir.
When you're done with this, can you actually do 76? Or look at it?
No, not until you guys have. And I don't think you guys have.
I have.
That's good for you. You hang on for everybody else.
I'm trying to help everybody else out.
How's that? Is that cool? 76, I mean, it sounds gross. They give you the image that you have to work with. So I want you guys to try that out before I do anything with it for you. Okay. So, please let this be simple. Here, look at this one. Here's one that they give you the function, but it's an interesting problem anyway. If anybody's going into 178, you'll be doing a lot of these kind of problems in the early going of the class. So read through this. Each grapevine, about 10 pounds of grapes in a season, when about 700 vines are planted. Now, why does this next part kind of make sense? For each additional vine that is planted, the production of each vine decreases by about 1%. If you put more stuff in there on the land, it's taking nutrients, so the other ones can't produce as much as they would have, right? So that's another thing where there's competing. You put more in, you're going to get more grapes, but then you get fewer grapes per each one. So there's some sweet spot that happens in the middle, right? With me? Okay, a few of you. Same guys that always let me know whatever's happening in their head. The number of pounds of grapes produced per acre. Now, why does this make sense? Where the hell did it get from? So they make
700 per acre, 700 plus N.
Yeah, 700 plus N, because that's how many more vines I'm going to put in.
Yeah,
And then each vine makes 10 pounds
minus the
minus 1% of.
traditional.
Exactly. Cool. I like it. So they did that work for you. And again, I would not do that work for you. I would have the setup and say, find an area, find an amount equation, find an equation that models how much you would get. Yeah.
I'm just going to ask, you're going to make us figure
Oh, hell
out.
yeah. Aw. Okay. Alright. So then how would you go about finding the number of vines that should be planted to maximize grape production?
Multiply them.
Yeah, multiply this out. Not surprisingly, you get what kind of thing? Quadratic. It's crazy. So then you got your B and your A. You can attack it like always. You kind of with me? So this is the kind of analysis people didn't know they could do, and then math came in and said, here, this is what you're kind of doing wrong. We can really tweak this and make it much more efficient. Kind of with me? So that's one little area where obviously math has something to do with everything, trying to make things more efficient. Okay, maybe. So most of these, they actually give you the function that you're working with, which is really nice. Just so you get used to negative V over 2A stuff. But definitely realize I'm going to give you stuff like this on the test. A little preview of 3.2, and then I'm going to head out a little early. Just because. So 3.2, 3.2 is full. I mean, I swear to God, 3.2's got a lot in it. So if there's ever any time you want to actually read ahead, this might be it. All right, so I'll see how many of you guys can actually do that. So they have a little bit of about transformations in there. So we talked about transformations. What's really important is this kind of thing. This is the one thing I want to do from here today, is this. Obviously, if I have this function, what will it look like?
A parabola, a wider parabola.
Yeah, it look like a parabola that kind of goes up a little bit slower here and then faster there. I might have overstated it, but too bad for me. You guys with me? So what the hell happens? So this section is going to talk about what happens if I have this other function that's like this, but then it has other terms in it. So one thing I know for sure that's going to happen, and this is a very interesting idea, and I want to introduce some new notation that's going to especially help those of you out there going into calculus. And for the rest of us, it's just going to help us out right now. I want to talk about something called end behavior. So the end behavior for this guy is this, right? Go. So the end behavior for this guy, it might seem like it's really hard to tell because there's all this other crap in there. But end behavior, what does that kind of mean? Do I care about what's going on in here? I care about what's going on at the ends, which means let x get really big, positive or negative. Are you with me? So end behavior is all about what happens when, oh Jeff, you can't write, we're shit. What happens when x gets big, positive or negative? So here's a symbol that I use to represent that that's happening. We already know that I'm talking about letting x get really big means let x approach what number or what idea? Infinity. So let x go to infinity. And here's how we say x goes to infinity. A little more precise way of saying this is I want to know what f of x does as x goes to infinity. So what I say is, what's the limit as x goes to infinity? Right? So when x gets really, really big, when x gets huge, which thing in here is more important than any of the other ones? Yeah, the x to the fourth. That's going to... a trillion to the fourth power is stupid bigger than a trillion cubed. Right? So like my whole thing, if I'm Bill Gates, $1 doesn't mean that much to me. Right? Whereas if I'm me back when I was in grad school, I scrounged through my car and $1 saves the day for me. Yay! I got $1 in change I could eat. Right, so it all depends on relative. So this guy, relative to the rest of them, will grow so much faster. So when x gets really big, these effectively go away compared to this guy. So you can imagine 1 billion to the billionth power raised to the fourth power minus this stuff, that's barely going to touch it. Yes?
So whatever's the biggest exponent, I
Yes.
guess, that's what's going to
That's what rules the day. Exactly. So the end behavior will relate to whatever the largest degreed term is. So in this case, the limit is x goes to infinity of f of x. It goes to infinity like x to the fourth, because that's the highest degree. And of course, the actual limit would be infinity. There is no limit, but what's more important to us is the shape it takes. So what's really weird about this dude, now these things will do a lot more when you get really, really close to 0, because then that will be smaller than all of these, won't it? Because anything close to 0 to the fourth power is getting even smaller. So when it's close to 0, this is going to do some weird ass shit, right? But when I get out here, it's got to look like this. In the middle, it can do all kinds of weird stuff. Now, how many turns do you think it could take total? How many turns does this take? 2. X cubed plus other crap could look like this. You could have... And think about it. How many intercepts, how many solutions could there be if it's a third power equation? 3. 1, 2, 3. Right? Whereas here, this could go like that and have 1, 2. So how many turns? A third power has 2 turns. A second power has 1 turn. So a fourth power is going to have at most 3 turns. So I could turn once, twice, 3 times. And then I can match back up with my end behavior, right? You guys kind of get the idea? So this idea of end behavior, if I give you a problem like this, let me make it look. There you go. A little negative squared up. What would the end behavior be? How are you going to tell?
The fifth.
No. What's different between that and this? This has been multiplied out. So if you did multiply it out, what would be the highest degree that you would see?
10.
No. 7th. Because we had powers, right? Negative x squared, and then this would come out to x to the 5th plus blah, blah, blah. Smaller degree term, so the highest degree I'd see is to the 7th. Negative x to the 7th, right? So the end behavior here would go like negative x to the 7th. What the hell does that look like? X cubed, any odd power looks like what? Do your hands. I love it, see? I love it, sweet. I'm trying to think in your perspective. Your perspective is that, right? No. Yes, that's you. That looks right. So negative that would look like that, right? So negative cubish. So cubish looks like this. Negative cubish looks like that. And in the middle, it's going to have how many at most terms? 6. It could have no terms. It could be, that would just be like that. But this is definitely going to have some terms to it. You guys kind of with me here a little bit? Little tiny. There's a ton left in section 3.2, believe me. But I wanted to at least step a little bit into it. This idea of end behavior is huge. That's where we always start. What does it look like at the ends? So that when I do this by hand, I know I'm in the right way if I end there. If I end there, I'm screwed. Oh, shit. So I know something went wrong. Okay, that's it. See you guys tomorrow.
you have my corrections?